Okay, so piecewise functions, day 2. Nothing too crazy today, just higher complexity of functions, I would say. But the process is the same. So, we've got our graph here again. You can't see the grid on your paper, it's really faded, but try your best to approximate. So we got x is x less than -4, between 4 and 0, and then greater than 0. So this is x plus 6 all squared, negative absolute value x plus 1, and 4 minus x squared. There should be like commas in between here to show just where the function ends and the region begins, especially for that one because they're like really close together, right? Okay, so x plus 6 all squared is a parabola shifted which way? To the left 6. Okay, so normally in a parabola, the vertex would be where? On the x-axis where? Huh? At 0, yes, at the origin. And so now if we're going left 6, where would the vertex be now? At -6. Yeah. So here's our vertex of the parabola. And so now we're just graphing our parabola parent function. So 1 squared is 1, 2 squared is 4. Got an open circle there. And 3 squared is 9, etc. If we were just graphing x plus 6, like if this wasn't a piecewise function, we were just doing that, we would just graph it normally. We would see the full shape, and it would still be in the same place. So the fact that this is a piecewise function has nothing to do with where that parabola is. Yeah, it's the same thing. Yeah. Okay, so our absolute value function, that's in the middle there. Okay.
Sorry, just double checking. The reason it's open on the boundary line is because it's not, or like it's not, it's just less than sign.
Yep. Yep. Okay, so our absolute value function, what's happened to that one? What kind of transformations are we doing to our absolute value? Left 1, and yeah, vertical flip reflected down. Okay, so normally the vertex of absolute value is where? The middle, center, the origin. So now it's left 1. Normally it goes up and has this V shape, like that. So if we're going left 1, there's the sort of point of it, and now it's going down. Closed circle on 4, open circle on 1. Again, since you guys can't really see the grid on there, you want to take -4 and plug it in. You get -3. Take 0, plug it in, and you get -1, just to be sure of those points right there. So obviously a lot easier with the grid. Okay, then for minus x squared, that's a parabola. What's happening to it? Shifting. Right? 4 minus x squared. Which way is that shifted? Not left. It's not right. It's going up. It's going up, and then it's being flipped. Yeah, so another way that we could write this is negative x squared plus 4. Same thing, right? Yes, it's going up 4 and then going down. So our vertex is up at 4, and then we just graph our parabola points. So 1, 1, 2, 4, except we're going down. Potentially going to vertical. Yeah. Okay, so one thing I want to emphasize with this is that these regions of where the graph exists have nothing to do with where the graph is shifted. They are completely separate. This is shifted to the left because the equation says shifted to the left. Our full parabola, again, would look like this. If it was not a piecewise function, that's where it would be. Because it is a piecewise function, we just chop that right end of it off. Our absolute value function is shifted to the left because the equation says it. Has nothing to do with the region. So if we were just going to graph the full thing, it would look like that. Since it's a piecewise function, we're just taking part of it. So that's a common point of confusion that I see often. But those regions just say like which part we can see. It has nothing to do with where it is. Questions on number 2? Okay, you guys do number 3. All right. So -2. To the left, we've got just a horizontal line with an open circle at -6. And then on the right side, we've got our cubic function shifted which way? Left. So there's 0, 0, 1, 1, 2, 8, and then -1, -1, closed circle there. Bless you. And just a reminder to remember, like, making a connection back to polynomials, first day of school. X plus 1 cubed means a 0 at -1 with an inflection point through that 0, which is what the cube function is. So just a little reminder there. Okay, do number 4. All right, let's check. So we got -3 and 3. We got y equals x. We got y equals 3 over x. And root x minus 3 plus 2. Okay, the line y equals x, what's the slope of that line? 1. Slope of the line is 1. So the y-intercept would be what? 0, yeah, if we saw the full graph. So again, with a grid, we could start there and just trace it back. Slope of 1. Without the grid, you can just plug in x to figure out where it hits that boundary line. If we plug in -3 to x, well, then it's just -3, right? So open circle there. And as best you can, just try and do a slope of 1. Okay, this middle region here, 3 over x. What I would do for this is just plug in points that are going to be whole numbers, such as 1, 3, 1. What else? -1. and negative. What happens if I plug in 0?
Zero.
What? No, undefined. It's an asymptote. Okay, rule number 1 of math, don't divide by 0. Rule number 1 of domain, don't divide by 0. Don't. Okay, I want to just talk about this for a sec. So if I solve this, this to me means 3 times 1 over x. If I take a function and multiply it by a number, what kind of transformation is that? Stretch. Yeah, this would be a vertical stretch. This function is unique because this also equals 1 over 1/3 times x. Do you guys agree with that? If I see a fraction multiplying x in a function, what kind of transformation does that look like? That is a horizontal stretch. So remember, x is backwards. If we multiply x by a whole number, that's a compression. If we multiply x by a fraction, it expands. So this is a horizontal stretch. So this parent function is unique in that if you stretch it, it stretches vertically and horizontally at the same time because of the way that fractions work. This is not how I would do the transformation, but we could do it this way because normally we have our point at 1, 1. So if we stretch that point vertically and horizontally by 3, it goes 1, 1, so now it becomes 1, 3. That's the vertical stretch. Or it was 1, 1, and now it becomes 3, 1. That's the horizontal stretch. So just another way to think of it. Again, I would just plug in points, but you could do it that way. Okay, last but not least, we've got our square root function shifted which way? Right 3. Up 2. Right 3, up 2. Okay, normally, square root function starts at what point? 0, 0. So now it's going to start right 3, up 2. We do have a closed circle. It's going to be right there on that boundary line. So that's 0, 0. So then we have 1, 1, 4, 2, 9, 3, which we don't quite have space for. It would be like over there. And look like that. Questions on that? Give me like a thumbs up or thumbs down. How are we feeling about graphing piecewise functions? Okay. Nice. I like that. That's a good place to be. Let's go to the next page, which doesn't quite look like this. All right, let's get some more practice. You guys do 5 and 6. All right. So 2 absolute value of x. What kind of transformation is that? Huh? Up 2 over 1. Yeah, so it's good. It's basically going to change the slope of those lines, vertical stretch. Okay, so again, the best way to figure out where it's going to start exactly is just to plug in -4. So absolute value of -4 is 4. 2 times 4 is 8. It's just going to start up here, the closed circle, and then we're imagining the V shape is doing this. So sometimes it's hard to remember which part of the absolute value you're at, but you want to go back this way. Okay, for square root of -x, if the negative sign is next to x, what kind of transformation is that? It's one of these. So it's a horizontal flip, right? Negative on the outside, affects the y coordinates, vertical flip. Negative next to x affects x, horizontal flip. So it's just going the other way. And notice there's nothing between 0 and 2. For that one too, you could also just try plugging in some points, right? If I plug in -4, it becomes 4 and square root of 4. Okay, and then our cube root function shifted which way? Right 2, down 3. So right 2, down 3. There's our origin points. And there's 1, 1, and so it's cube root, so we need to go, instead of 2, 8, we need 8, 2. So we're going like that. The full graph would go like that. It's easy to mix up cube root and the cube function.
Oh, wait, no.
Questions on that one? All right. Okay, so at number 6, we've got one of those like from the homework where we just have 1 point. So we're just going to have a point there at 0. We plug in 1, we get 0. And then we've got our other function. So just like that homework example we saw. Okay, so absolute value shifted which way? Right 3. Okay. So that would be like here, going like this. Again, if I just plug in 1, I see I'm at 2. I've got my slope of. Oh, that should be an open circle. Okay, and then 2 root x. What kind of transformation is that? Yeah, it would be a vertical stretch. Okay, is 2 root x shifting sideways at all? No. So we need to imagine it starting at the origin, and so then as I go to the right, instead of 1, 1, what would I have? 2, 1? 1, 2. Okay, so that would also give me an open circle right there. And then as instead of 4, 2, what am I going to have? 4, 4. Yeah. And then what would the next point be? 9, 6. So we're getting this shape right there. So again, we're graphing it as though it started at the origin because the function was not shifted. You just only see part of it. So this function is almost continuous. Morning. Except for that point floating below. Question on that one? All right. Let's take a look down the page at these writing equations. So similar thought process when we're writing equations here. You know, we have f of x equals, we've got a big old squiggle bracket there. And we start with the leftmost part, go in increasing order. When we're looking at something like this where it's a parabola, we just want to check and see that the points that we can see on the grid match the points of the parent function. If they don't match, then there would be some kind of stretch or something that we would have to account for. In this case here, do those points match the parent function? Yes. Yeah, they do. Are they in the same location as the points of the parent function? Yes. So this is the parent function. For x is less than or equal to 1. And then for lines, what's the slope of that line? 2. So it'd be 2x plus 1, yeah. 2x plus 1. So we can just trace the slope down to see where it would hit the y-axis. See, that's our y-intercept of 1. Remember that if the y-intercept is not a whole number, we could use this point as like a transformation and say, okay, this is 2 parentheses x minus 1 plus 3, and treat that point like it's been shifted, and then distribute. So that's our other way that we can do lines on piecewise functions. Okay. Questions on that? All right, you guys do this one. Hey guys, there's 3 parts to this graph. See on the board here? We've got this horizontal guy that's a little bit hidden. Sort of hard to see.
I've been holding that in all year. I'm not sure about the 0, but it's better than the 0. Yeah.
Or is it week 2? You don't. So I'm gonna say week 2. So
Yeah.
All right. That's what I got. So f of x equals 0 between -5 and -2. We've got a negative parabola shifted up 4. No stretch though, no left or right shift, just up 4 going down between -2 and 1. And then our line is -x plus 3 between 2 and 5. We do have an option to move this negative sign right there next to -2. We could put it over there if we wanted. And just make that less than -2. So we have an option for that one. We need exactly one negative sign at -2. So they can't both be. Questions on that? Okay. We'll come back to this max and min next class, but I want to go back to this question here, which is on the previous page. Okay, so our first one here, so basically we've got two graphs, f of x and g of x. And our first one here, we want to do g minus f of 10. So remember back in the day, like last week, when we had a function, f of x, let's say was the point 1, 2, 3, 4, and g of x was like 1, 3, and I don't know, 2, 4. So if we wanted to do g minus f of x, we could only do that subtraction for which points? Common
X factor.
Yes, the ones that have the same x, exactly. Because basically it's saying it's the ones that have the same domain, the ones that exist in the same places. So when we do that, we would be subtracting what? The y values, exactly. So for the x's they have in common, we subtract the y values. And here's just another way to think about that. When we say f of x, we could also write what other letter? Yeah, we could write y. And what about when we do g of x? Also y, right? Those both are representing y, the y coordinate. So when we say g minus f, we're saying y minus y for when we have the same x. That's just like what that means. So that's why we keep the x the same, and we do 2 minus 3, we do y minus y. So if I wanted to know, well, let's say I wrote it like this. Let's say I wrote it as g minus f of 1. How would my answer change? In this case, instead of x, I have 1. So I'm giving us an x value.
You plug 1 as an x value into both of the graphs that you get, and then you just try to y accordingly.
Well, I'm looking at just at this one right now.
Oh, subtract. You subtract those two.
Subtract those two. So our answer would be -1. It wouldn't be the points anymore because I'm plugging in x. It's like I'm plugging in x to this right here. So that's basically what you said is what we're doing for the next one. So when I say down here, g minus f of 10, I'm going to go to where x equals 10, and I'm going to subtract the y values. Brandon. I'm doing oh, g minus f is 1. Yeah. You're right.
I was confused, like,
I was doing f minus g yesterday, and I just decided to switch it up today. I don't know why. Logs. Good catch. Okay, so same thing for the graph. We go to 10, and we do g minus f. We do the y coordinates subtract each other. So at 10, f of x is negative 5. And g of x, negative 3, it looks like. Yeah. You can see a little clearer on mine. So g minus f will be negative 3 minus negative 5, which equals so we subtract the y's when x is 3. You guys do letter B. Okay, so we're going to x equals 6. What is f of 6? Negative 5. And what is g of 6? All right, so we're doing negative 5 times 1. Okay. So the next one, g of f inverse of negative 3. So we got composition of functions, we got inverses. They're still around. Is this the graph of f inverse? No, this is the graph of f of x. Yeah, this is f. Okay, so what would I need to do to this graph to get f inverse? Flip the x and y values, exchange them, yep. Or graphically reflect over the line y equals x. But flipping the x and y values is exactly what we want to do here. So if I'm trying to find f inverse of negative 3, does that mean I go to this graph and plug in negative 3 for x? No. I need to plug in negative 3 for y because they're switched. We have the graph of the regular function. We're looking at the inverse. We need to go to y equals negative 3. And our result is going to be the x coordinate because we're switching x and y. So our x coordinate there is 4. So now we do g of 4. And g of 4 equals math. So last but not least, this looks really complicated, right? 3g of 2f of x plus 1. But it says at x equals 4. Yeah, so we're starting with x. Where can I plug in x? Where does x go? In the equation where? Where there's x, right. There's only one place. So what function is it going into? F. So we're going to plug 4 into f of x, and we're going to get, well, we're going to get negative 3 because we just used that point, actually. So that means f of 4 is negative 3. So this becomes 3g of 2 times negative 3 plus 1. Wait, plus 1? Minus 1, right? Yeah. Wow, apparently it's supposed to be plus 1. Yeah. It's definitely -1 on the paper. Okay. But it appears to be +1 on this digital copy. It's just really, really faded. We'll just go with -1. Okay. So what's 2 times -3 minus 1? -7. So this is 3g of -7. What's g of -7? Negatives. I'm getting -4. -4? Could be -3, -4. On mine, it's a little easier to see. It's -4. So we're just going to do 3 times that value, which is 3 times -4. So our final answer here, -12. Okay. So not necessarily a simple process, but also not as complicated as it looks. All right, we just kind of go step by step. We plug in 4, get the result, do the math, plug in -7, get the result, do some more math. Okay, that is it for piecewise functions.
First part.